Graphics chips started as fixed-function graphics pipelines. Over the years, these graphics chips became increasingly programmable, which led Nvidia to introduce the first graphic processing unit. The biggest constraint in using the GPUs for general purposes was that they required the use of graphics programming languages like OpenGL and CG to program the GPU. Nvidia realized the potential of bringing this performance to the wider community and invested in modifying the GPU to make it fully programmable for scientific applications. Plus, it added support for high-level languages like C, C++, and Fortran. This led to the CUDA parallel computing platform for the GPU. Whilst the CPU is comprised of cores designed for sequential serial processing, the GPU is designed with a parallel architecture, consisting of more efficient yet smaller cores that easily handle multiple tasks in parallel. Simpler computing cores allow GPUs to pack many more cores into a chip than a general-purpose CPU. Additionally, GPU architectures have specialized their memory architecture to support high-speed data streaming for image processing, important for broadcasting. Nvidia GPUs contain one or more hardware-based decoder and encoder chips separate from the CUDA cores, which provides fully accelerated video decoding and encoding for several popular codecs. GPU hardware accelerator engines for video decoding, NVDAC, and video encoding, NVENC, support faster than real-time video processing, which makes them suitable for transcoding applications in addition to video playback. Cinegy version 12 moved the compositing stage of the playout pipeline to optionally reside within the GPU, which had great benefits for customers that wanted to use our integrated branding system for adding graphics to the output, or were using the very convenient and efficient Nvidia NVENC H.264, H.265 encoding blocks. As people pushed the boundaries of the engine, the computation overhead of taking source material decoded within the CPU became a limiting factor. To reach the dream of 8K60 at 10-bit, we knew we needed to cure this. As a result, we created a way to connect the input stage of our media layer to the compositing stage without moving over the CPU at all. Of course, we went further with integrating our excellent GPU pipeline into Cinegy Capture to both decode the input IP feeds and encode the output files, and Cinegy Convert that uses GPU pipeline for media transcoding. GPU acceleration made our migration to cloud platforms smooth and seamless, and today our complete media production workflow can be run from the cloud. Cinegy Multiviewer is not an exception. We've been using NVDAC to decode IP feeds as well as NVENC to encode the IP outputs ever since version 11. But recently we have made significant improvements in Multiviewer's GPU pipeline, and this is mainly what this video is going to be about. Bored by the lovely pleasures of year 2020, we challenged ourselves to build a high-density multiviewer server able to decode and display an impressive 100 full HD feeds. For this we used 4 Nvidia Quadro RTX 4000 cards in a 64-core AMD Threadripper workstation. We used our own Cinegy components to generate and send 100 of those feeds over a 10 gig link to this beast of a machine. What seemed to be odd, that even with the stunning performance of 4 RTX cards, the CPU load during this experiment turned out to be suspiciously high, while at the same time, the GPU's load seemed to be clearly slacking off. So, where could our resources utilization be improved? We were confident about our NVENC and NVDAC workflow, so we ruled this out as the potential bottleneck and focused our attention on another component key to Multiviewer's performance: scaling. During the video frame processing required for scaling, the GPU would decode an uncompressed video frame of 4 megabytes of data for full HD. This data goes through a number of copying cycles from GPU to RAM, then to the CPU, just to be passed back to the CUDA cores of our GPU's main chip for processing. The main idea around improvements was about reducing the amount of these data copying operations and concentrating data processing in Multiviewer's master GPU pipeline. The results of my tests on the next slides will illustrate just how brilliantly we coped with the task of optimization. The idea of my task was pretty simple. Load my test multiviewer servers with IP feeds to operate at hardware capacity using GPU decoding, take the measurements, repeat the test with the yet unreleased Multiviewer 21, compare the results. I chose a server with a 7-year-old Intel Xeon chip and an Nvidia Quadro P2200 board, almost matching the specs from our system recommendations. The P2200 card can handle up to 24 H.264 HD interlaced streams. I fed these 24 to the input of my Multiviewer 15 as multicast RTP over a 10 gig LAN, and I set all the streams to be decoded by a GPU. The CPU load in this test fluctuated between 45 and 50%, whilst the GPU was operating at 55% load, most of which is the video engine load attributed to Nvidia performance. I took a quick look at GPU Z readings to see that the main chip doing scaling was barely engaged. Next step, upgrading Multiviewer to a development version 21 that includes our changes to scaling, and voila, we see the CPU load significantly decreased. CPU now running at 25 to 30%, while the GPU is now pretty busy at 75% load. Having had another look at the GPU Z sensors, I saw that the general GPU load has increased, whilst video engine stays pretty much where it was in Multiviewer 15. The main chip's engagement is a clear evidence that our optimization is working. CPU load decreased by half, and an extra 20% of GPU utilization sound good for starters. However, these results do not look as impressive on pure hardware. Multiviewer 15 scaling simply doesn't eat out as much CPU on this setup. What's going to happen if we try the same on virtual machines in the cloud? I chose an AWS G4 instance. Equipped with the Tesla T4 GPU and a 24-core Xeon Platinum CPU, they offer great performance for a relatively cost-effective price. Additionally, it literally takes a couple of minutes to get an EC2 instance ready for production. Check out our YouTube video from last summer, where we spent literally 10 minutes using Terraform scripts automation to launch 150 playout channels in the AWS environment. Similarly to my previous test, I started with Multiviewer 15 and fed it with 12 HD H.264 SRT streams delivered over public internet. Multiviewer 15 made the CPU work really hard at 94%, while my Nvidia T4 was slacking off at 40% load. And even though decoding SRT streams eventually produces more CPU load, I've got to remind you I set my Multiviewer to use GPU to decode each of those input streams. An upgrade to Multiviewer 21 introduced quite a dramatic shift in performance. See for yourself. CPU utilization went down to just 42%, while GPU started working at 86%. Pretty much flipped the processing from CPU to GPU. This EC2 TestKit is a good indication of how an entry-level GPU instance can be a great and cost-effective choice for your cloud monitoring. Running all your decoding for 12 streams on CPU only at a comfortable load would require at least a G4 4x large instance at £1.55 per hour. GPU offloaded decoding for the same number of streams is already an option for roughly half of that price with G4 2x large instances. And with the optimizations introduced, it leaves even more CPU headroom to neatly carry out other operations. If you don't care about headroom, you could potentially get away with a G4 X large at even lower rates. Let's return now to our challenge of monitoring 100 HD channels in a single box. Remember, I was using an amazing 64-core AMD Threadripper with 4 Nvidia RTX cards. Unlike the good old P2200, which only has one Nvidia chip, each of these cards offers 2 Nvidia chips, almost twice as many CUDA cores, and extra 3 GB of memory, providing a level of density required to handle that many streams in a parallel. So, I streamed 100 5 meg HD H.264 feeds to the Multiviewer 15, letting each of the cards decode 25 streams. The CPU load was at 15%. While this seems low, this is definitely too much for a 64-core Threadripper with GPU offloading enabled. At the same time, the GPUs that were supposed to be busy with some heavy lifting were taking it easy, operating at 60%. The tiles on the Multiviewer mosaic did not look smooth either, and the quality could be improved. Let's see whether we spot any improvement with the same setup running Multiviewer 21. The CPU load dropped down to 6%, while GPUs started working way harder at 80 to 90% each. This resulted in Multiviewer pips having pristine quality and no jitter whatsoever. Challenge complete. This is not the end of it just yet. Having such an extraordinary machine at my disposal, I thought how much power this beast actually consumes, which made me think whether the optimization in Multiviewer had any impact on its energy efficiency. Having heard a lot of rumors about RTX GPUs being hungrier for power than the CPU, I decided to try and check whether the new Multiviewer can bust that myth. A 64-core AMD Threadripper chip seems to be a great rival for my multiple GPUs, so same challenge, but this time my focus will be on power consumption rather than CPU and GPU loads. I used a simple approach, with a watt per hour wall socket meter. I decided to skip filtering the noise, like the operating system, background processes, etc., and focused on measuring general consumption, assuming that 90% of power draw would be caused by CPU or GPU work anyway. I started with 50 HD feeds decoded in Multiviewer 21 by CPU. That is a number of streams it can handle without stuttering. Working at 65% load, the Threadripper scored 404 watts per hour. I then did the same with 50 HD streams fed to Multiviewer 21, this time with GPU decoding enabled. The meter reading showed 463 watts per hour, and got me worried that these numbers won't be convincing enough as an argument for energy efficiency. However, I thought it would be unfair to not use the joint capacity of my 4 GPUs at its fullest, so I ran one last test with 100 feeds decoded by GPUs. And this is exactly where I can conclude that better GPU utilization introduced in Multiviewer 21 is a step to make our decoding energy efficient. 705 watts per hour was the meter reading. Look at per stream monthly costs. GPU decoding is clearly a way to save you some money. And don't forget that my Threadripper was only able to decode 50 streams without stuttering, compared to 100 streams decoded by 4 GPUs. Now imagine building a machine that can monitor 100 HD streams just with CPU decoding. That would probably require adding another Threadripper 3990X to your server. Not just it would result in doubled power consumption, but also cost you around £4,000 in purchase price. The cost of our Threadripper with 4 Nvidia RTX GPUs set up is roughly £6,500. Given how low the CPU utilization was with GPU decoding enabled, it's safe to assume that one might get away with a 24-core chip for a similar server. I looked up a 24-core AMD chip of the same generation and thought Threadripper 3960X would be a fair comparison. The combined cost of 4 Nvidia Quadro RTX 4000 boards and an AMD Threadripper 3960X would barely hit the price of a 3990X chip on its own, and would still be able to monitor 100 HD feeds at a comfortable load. GPU decoding doesn't just offer a supreme density, higher cost efficiency, and better performance. It's also a way to reduce your carbon footprint by using energy-efficient solutions. In summary, here is a combined graph of my test results between Multiviewer 15 and Multiviewer 21 on different hardware. As can be seen with the changes we have introduced, the CPU load has been reduced more than by a factor of 2 across all 3 test kits. At the same time, in each of these cases, we achieved an amazing improvement in GPU utilization, no matter if it's a new RTX 4000, older entry-level P2200, or cloud-based T4. Yes, now is a good time for broader conclusions on this entire experiment. GPUs are a good way to breathe some new life into your existing hardware. Even if your server has a 7-year-old CPU like mine in TestKit 1, adding a modern GPU like a brilliant RTX 4000 to your setup will cost around £800. Special thanks to crypto miners, it will help to keep your hardware delivering valuable functionality for another few years. GPU acceleration is an absolute necessity for cloud deployments, as this will drive higher density, better performance, and more cost efficiency. CPU-based computing simply can't offer you the kind of value for money that you get with GPU instances. Even with multiple GPUs working in a parallel for maximal density, you get less power consumption at a lower cost. Multiviewer 21 is going to be even better and faster for your monitoring. Thanks for listening, and I hope to see you all on trade shows really soon.